Thank you for joining our second webinar in our five-part Open-NFP Spring Webinar Series. Today, Pervez Akhtar and Christo Klug are going to present measuring a 25 and 40 gigabit per second data plane. This webinar will cover the basics of performance testing. Pervez and Christo will discuss how configuring systems correctly is essential to characterizing the performance of SmartNICs, the configuration of BIOS, CPU allocation, OS and VM parameters, and choice of traffic generators and typical test topologies will be described. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page of the OpenNFP.org website. Pervez Akhtar has been the VP of Performance Test and Launch at Netdevs for the last 5 years, where he focuses on accelerated security appliance and managing performance characterization and test team. Christo Klug is a senior engineer at Netdevs, where he has been for the last year, focusing on performance testing of Netdevs' accelerated product suite, regression testing, and competitive benchmarking. Let me describe Open-NFP before I turn it over to Pervez and Christo. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems, and direct support from our engineers in a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 40+ universities and companies working directly with Open-NFP through projects. Over to you, Pervez.
Okay, hello. So we'll start with the title. As you see, we're going to talk about measuring a high-speed data plane. Although the title of the talk is 25 and 40 gigs data plane, very little of what we're going to talk about is specific to a particular speed. What we're going to describe to you are the techniques and characteristics of testing something that operates at 25, 40, or even 100 gig data plane. Before we get into the details of the talk, one of the things that you need to do is to plan out what you're going to need in order to do the testing and what your goals are. So let's talk a little bit about the objectives that you might have. So a typical topology for testing might look like this, where you've got one or more virtual machines running on a hypervisor, a SmartNIC of some kind underneath, a network switch connecting them to the two, and the data path going up to via the SmartNIC up to other VMs. Now, it becomes very important to understand what it is you're going to try to test, because the configuration and the setup is going to be different in different cases. Are you trying to measure the VNF itself? Is it a product quality VNF which has already been tuned and you know what performance you're trying to achieve and prove, or is it an experimental VNF and you're just trying to establish what it can do? Do you care about small packets, or do you care about large packets, or are you trying to generate some kind of realistic mix of traffic? Further, are you trying to measure the very best case that the system can achieve, or are you trying to measure something that is going to approximate a real deployment and a real user use case? What are you trying to measure? Are you trying to measure the number of packets per second that you can achieve or the throughput. Of course, the throughput and the packets per second are complementary. Do you need to measure how many packets are dropped, or impose a limit on the threshold, the amount of packets that can be dropped? Further, do you care about latency of packets and jitter? Because that will dictate what kind of equipment you're going to need. And finally, what's your budget? Do you have access to high-speed traffic generators, or are you trying to do this with minimal resources? There is no one solution to any of these combinations. What you're going to do is going to depend very much upon what your constraints are and what you're going to try to measure. But what we're going to try to cover is the basics of which characteristics are going to be the most important in doing these measurements. So obviously you'll need a system with a NIC installed, and in our talk we're going to focus on measuring the data plane, a high-speed data plane going through the SmartNIC. In our configurations, typically the system needs to support SRIV and ARI. You will need, in most cases, a large amount of RAM because when you start running multiple VNFs and multiple VMs, you need to allocate an appropriate amount of RAM to each of those VMs, and small systems just don't make the grade. Further, you're going to need something with a fairly substantial number of CPUs, possibly even a multi-CPU system. And you're going to need those CPUs to be fairly high clock rate in order to support the data rates, whether it's for generating traffic or whether it's for handling the VNFs themselves. The goal here is that you want to be measuring the data plane. You don't want to be inadvertently bottlenecked by the resource limitations of the system or the operating system or the VNFs themselves. You've got a choice of various different traffic generators. We use many of these combinations that you see here on this slide. We will often use hardware-based traffic generators like the Ixia and the Spirent. These are wonderful pieces of equipment because they can do a wide range of measurements with a fine degree of control. If you're doing things like latency and jitter measurements, these are almost essential for doing those kind of measurements. The downside is they're quite expensive, so you may or may not have access to them. Even within our organization, they are a scarce resource. The next level is using software-based traffic generators, typically DPDK-based generators that can take advantage of SmartNICs and use some hardware assist facilities, but at the same time generate small packets at very high rates and very easily get to line rate with large packets. The two ones that we use typically here, MoonGen and DPDK Packet Gen, they each have slightly different facilities, but the common theme here is these are packet generators. They're open source, they're supported by the community, they use DPDK as the transport, and they are scriptable and controllable via a language called Lua. If you don't have access to those things, then Linux comes with a variety of different tools out of the box. You can use iPerf, which has gone through a number of iterations, so we'll just generally refer to it as iPerf, but you will want to be using the latest instantiation of that, or NetPerf. Now, iPerf and NetPerf, very easy to use, readily available, but in order to get high rates, you'll need to play various configuration tricks and use multiple instances or multiple threads in order to get the necessary performance. So a little bit more about the traffic generators here. With the Ixia, you've got anything from 1 gig interfaces up to 100 gig, very flexible on packet size. You can do a full range of measurements, and apart from the expense, these are very easy to use. The DPDK packet generators, MoonGen advertises itself as about 15 million packets per second per CPU core. So if you're going to be testing a 40 gig data plane, you're going to be needing to allocate for small packets 6 CPUs in order to get to the appropriate rate. So as you can see here, this is why you get to needing memory and CPU resources for doing the testing. And if you're trying to test 100 gig, you can probably get there with MoonGen, but you'll find it much easier with the hardware-based generators. So we typically use DPDK, PacketGen, or MoonGen for anything from 1 to 10 gig, maybe even 25 gig, but for the larger rates, 25 gig and up, we typically use the Ixia. These generators can measure the packets per second or the throughput as you wish, and MoonGen in particular can take advantage of hardware assist to do latency measurements as well. You can control these via Lua scripts, Lua programs, but installing DPDK-based generators does require you to compile them on the Linux system and configure the drivers accordingly. iPerf and NetPerf come with most Linux systems. They're out of the box. You can get low rates very easily. You can even get line rate with larger packets, but in order to get high rates with smaller packets, you're going to need to use multiple threads or processes, and the scaling there with number of threads is not necessarily linear. And you'll need typically in the configurations we allocate 1 CPU per thread or process. So you can end up using a lot of resources if you go this route for generating the appropriate traffic rates. But they're very, very easy to use, but the downside is getting the appropriate throughput can be quite a bit more complicated. All right, so I'm going to hand over to Christo here to talk about various possible test topologies that you might use for your tests.
Thank you very much, Pervez, and thank you, Carly, for the introduction. So when we get to the different test topologies, I think to reiterate the goal that we've showed previously is we mostly want to measure the fast data plane. There's both internal testing that we do for performance testing as well as external end-to-end system testing, and both of those hold merits, and both of them are the data is valuable for different teams and groups. When we look at two of the big groupings of test topologies, you've got your single device under tests, where everything basically happens on a single machine. The benefit of those kind of tests is that you can have a specific machine still with a SmartNIC installed, but potentially you don't need to have any network equipment other than an external traffic generator connected to it. With the dual device under test topologies, there you've got a bit more of a hardware requirement. You would typically use 2 different servers connecting either back-to-back or via some kind of switch to test different things, where tunneling would be one of them and bonding could be another one. We can go to the next slide, please. So additional single device and test topologies I've given here. Now all of these hold merit again for different kind of tests, whether you're looking at performing operating system specific tests within the VM or on a host, or whether you would like to test DPDK tools such as MoonGen or DPDK PacketGen and compare their results, or compare results of iPerf versus NetPerf. All of these different topologies would give you different results because the data plane is different. If I take 2 of the examples, say the one in the left-hand top, the port to host to port, in that scenario you have an external traffic generator which would generate traffic into an input port. It would go through the PCI bus into an application running on the host and then passed out again. So in that scenario, you don't have a hypervisor and there's nothing that goes into a specific VM. In the test case just below that, you can run one or multiple guest operating systems, which would be beneficial when you're testing traffic specifically in a hypervisor environment. Next slide, please. Here are the dual device under test scenarios where the VM to VM case is currently being mostly tested. There's a lot of people that would like to do testing in the cloud data center environments, and that have a lot of east-west traffic in your data center. And there you need to have a test setup where a specific guest operating system can send traffic out through the SmartNIC onto the network and then be received and synced on another VM. Again, with these setups, you have the opportunity to either connect machines directly to each other or connect them to a network switch where you can test additional features such as bonding and tunneling from one machine to a different machine. So the next section that we're going to cover gives a lot of different details. So just as a high level, I would like to go through them we're going to focus a lot on host and VM configurations, and we give details on the NUMA architecture, which is how the architecture of a specific motherboard, CPUs, and memory would look, and what you need to do to ensure that you get the best performance results. We talk about CPU allocation, which will give details on how to separate your different functional elements when running different tests to ensure that a testing portion is not affected by something running on the host or within a VM. And then we've got some additional BIOS settings that helps to improve performance, host boot settings that is additional to the BIOS settings, and some tweaks that one can do in interrupt management.
Okay, so the overall goal of configuring a performance test setup is to be able to isolate different pieces of the system so that each piece is running at full performance and is not interrupted or trying to share capabilities with other pieces of the system. And this is essential so that you can measure the throughput without getting variations in the throughput, or small or large variations in the throughput. The other basic principle is trying to take advantage of locality, so that if you're trying to measure best case performance, you're minimizing memory copies, memory transitions from one NUMA node to another. And then there are other sources of variations, such as system power management settings, where typically systems will try to conserve power, but that works against any kind of maximum performance testing that you want to perform. And then configuring the system to avoid extraneous interrupts. So, Christo, I think you're going to talk about the NUMA topology here.
Yes, so we've added this almost as the first portion of when we get to the host and VM configuration options, because it's very critical to determining how to set up everything on the machine, and it all begins with where you plug in your SmartNIC onto the system. So to give you an idea of the NUMA architecture of a machine, I've got an image here that shows the difference between a two-socketed system where there's two NUMA nodes on a single system. So what you would have is you would have your physical socket with a CPU on it with all its core and hyperthread partners on a single NUMA node, and then on the right-hand side you will have your other physical CPU with all its cores and hyperthread partners connected on a different node. Now, what the NUMA nodes basically reflect is how close is the CPU to the specific RAM. So they're grouped in these different islands called NUMA nodes. There are many different architectures that follow on this. You can have quad-core systems, but for the rest of the webinar, we focused mostly on dual-socketed systems, as those are the ones that's currently being used the most. When we get to the memory, it is important when running applications that spin to a specific NUMA node or that you use the memory and CPU of where the application is running. We'll also see that when you run an application that's affinity to a CPU that's on a different NUMA node, so the memory is being used on NUMA node 0, for example, and the processing is used on node 1, there's an increase in latency and also a great degradation in throughput. From a lot of high performance tests that we've run, we've seen anything from 30% to a 50% drop in throughput just by allocating an application incorrectly or on the wrong NUMA node. So as the last bullet point that we've highlighted is determine the SmartNIC NUMA affinity. Now this is every morning when starting work and selecting a machine to work on, that's normally the first thing that I would do is like on which NUMA node in this machine is the current SmartNIC connected to ensure that all of the pinning that I'm going to do for the day, that I do it on the right NUMA node. So we've got an example here of an output of a tool called LS-Topo. So this gives an example of a machine that we're using on a daily basis. It's a dual-socketed system that's got 64 gigs of RAM. And this diagram itself explains nicely on how the NUMA nodes are set up. So you can see from the top the amount of RAM and then the RAM amount for each of the NUMA nodes, and under that it shows you your physical socket, socket 0 and socket 1, and then all of the cores, CPUs included, and the hyperthread partners. So we're going to use this same diagram throughout the webinar to explain the different concepts, the concepts of CPU pinning and the concept of isolating different CPUs and also the isolation for VMs to use. I would also like to highlight here, I've seen some of the notes that's made. In this scenario, the numbering convention for the CPUs was even number, so it's on node 0, so it was 0, 2, 4, and on node 1 it was 1, 3, 5. But these are highly dependent. It's highly dependent on the actual manufacturer. So one can't just assume every time that if you've got the SmartNIC connected to node 0, that you can use all the even number CPUs. One needs to make sure what the actual architecture is for the machine that you're going to use. So as a second example, I've just taken the LS CPU output for two different machines, and here you can see for the first compute node, it's got NUMA node 0 and it's got CPUs 0 to 9 as the first CPUs for NUMA node 0, and then 20 to 29. Now, the 20 to 29 in this case is the hyperthread partners of the CPUs 0 to 9. So if you would like to pin a specific application on a single physical core, you would use a CPU, say 0, and then an hyperthread partner, in this case 20. And then for compute node 04 at the bottom, this is the exact same example as the previous slide where we had even numbers and odd numbers. So this slide just shows an example just how the NUMA architecture can be different on different motherboards.
Okay, so with respect to the techniques that we're discussing here, the allocation of CPUs ends up being the most critical factor in ensuring that you're getting the consistent results and the proper results that you expect. You must ensure that you allocate the CPUs in a reasonable way between the tasks, and that you isolate. So you isolate CPUs for dedicated tasks, and you pin your applications to the correct CPUs. If you've not done this correctly, what happens is that CPUs are being used for multiple purposes, and the throughput that you're trying to get through the data plane is going to be affected whenever that CPU switches to performing some other duty. So there's two parts to this. So Actually, there are multiple parts to this. As you'll see as we go through the details, you're going to have to partition the CPUs, and you're going to have to pin some of the applications and the VMs to unique CPUs. And then if you're using DPDK-based apps like MoonGen or DPDK PacketGen, in addition, those applications themselves can be configured to use specific CPUs. In fact, you must provide specific CPUs for those apps. But at the same time, you must ensure that those CPUs are not allowed to be used by any other tasks at the same time. Okay, Krista, you probably wanted to talk to this legend.
Yes, so with the CPU allocation, I always like being very visual, and it's the easiest way using some of these visual tools and outputs to show the different techniques of isolation and pinning. My whiteboard is always very, very full of different drawings and numbers, but no one else can read them, but I enjoy visual cues. So what we have here is the LS topo output. And what I would like to note is in this example that we say the SmartNIC is local to NUMA node 0. So everything that we're going to use in this example is just to say that the SmartNIC is connected to NUMA 0. So for performance testing, we're going to give all of the different resources that we need to allocate to do performance testing and put them on NUMA node 0. So I've got a black box that's been drawn out on both of the NUMA nodes. It covers most of the cores, and that's for isolated CPUs. Now, in the next slides, we're going to go through a technique which is a host boot setting operation where you can isolate CPUs so that the Linux kernel cannot use them at all. I've got a blue box that highlights virt.io relay CPUs. So in this example, none of the other processors will use the cores 1 and 2 of NUMA node 0 except virt.io relay. In this example, we've got 3 VMs that's running in this test. And they're highlighted with red boxes. In each of the VMs, there's also a different, a green color box which highlights 2 different logical cores that's being used for a DPDK application. Now, in the case that I was creating this was for an L2 forwarding application, but it can be whatever application you would like to use in your testing topology. And also the host and VM operating systems is using the non-isolated cores, and that's the orange block. And in each of the VMs, there's also an orange block which shows the Linux scheduler being pinned to a specific CPU so that you don't share any of the application load to ensure that your performance testing can give reproducible results.
Yes, and you'll notice that in this particular example, we're focusing on NUMA node 0. It is fairly typical if you're trying to get the best case performance that we will focus on configuring resources to use the same NUMA node as the node into which the SmartNIC is plugged in and avoid using NUMA node 1. Now, if you're trying to generate a very large configuration that is more representative of real-world usage, you will end up using both NUMA nodes, but you'll end up having to partition the resources between those 2 things. Now we're going to go through some of the more detailed things, and we're not going to step through all of the gory details here, but we're going to highlight which of these things you need to pay attention to in order to get satisfactory benchmark results. So we talked about CPUs. That's number 1. That is the thing that is absolutely critical for setting. A secondary thing that is important for benchmarking is making the appropriate BIOS settings. And these cover 2 areas. One is disabling all of the available power management capabilities of the processor. You do not want the processor to throttle down when there's a brief lull in traffic, and then when you start sending packets again, it takes it, while it takes it a very small amount of time to get back to full performance, during that time it will drop packets. So you want the processor to be running full throttle all the time so that it can handle packets at maximum rate. And to do that, the typical approach is to go through the BIOS and disable all power management saving settings, and further, depending on what your goal is, you may wish to disable hyperthreading as well, so that there is no sharing of hyperthread CPUs available, because while hyperthread CPUs can run at high rates, there is measurable impact at very high rates when the hyperthread peers are used. Further, the other aspect that you will want to disable in the BIOS is any forms of system monitoring, and server systems will typically monitor things like memory and other aspects of the system, and periodically interrupt the CPU and notify it of the state. And each of those interrupts, if it comes in at a time when you are trying to handle a high-performance data stream, will temporarily divert the processor from handling packets to handling that particular interrupt, and you'll see a blip in the traffic. So disabling all extraneous interrupts from the BIOS is important here. And so here we're listing some of the typical things that you might see in the BIOS. Now, BIOSes vary. One BIOS manufacturer may have different terminology or different settings available. So it's going to depend very much on the system that you have available. So here we set the power regulator to static high performance, while it was originally set to the dynamic power savings. And we're setting minimum processor idle C state to no C states, and minimum package C state to no package state. And then power profile was customer, but we're setting it to maximum performance. So we're trying to disable everything that might cause the CPUs to go into any kind of power saving modes. For interrupts, and again, these will vary according to the system that you're running on. And the examples we're taking here are from some HP systems that we've used in our testing. So here, the key thing that we disabled was memory pre-failure notification, and there may be other similar interrupts that systems do. It was enabled, and we set it to disabled. And in the different versions of the HP systems, they generate these interrupts at widely varying rates. On the HP DL380 Gen 9, it was every 60 seconds. On the Gen 6 and 7, it was every hour. And on the Gen 8, it was every 5 minutes. So it's going to depend very much upon your system, but clearly 60 seconds is frequently enough that it is very, very likely to impact your test and be visible in that test. On the older systems where it's every hour, it's going to generate mysterious blips, but be much less readily correlated with a particular test that you might be running. So it's important to turn all of these things off that are available to you. Further, we found that it was necessary not just to set these settings in the BIOS, but to also ensure that the Linux systems that we were using, we passed through these settings to Linux to also ensure that it honors the settings and will set the power management settings accordingly. All right, so I think we've emphasized that you need to ensure that when you manage the CPUs, that you isolate CPUs to different tasks. You shouldn't use them for more than one task. You can allocate some for the host OS. If you're using XVIO, you'll want to allocate a certain number of CPUs for that. If you're using VMs, you dedicate one or more CPUs for the guest OS, and you'll dedicate CPUs for the VNF or the application or the traffic generator. And you'll isolate each of these out and ensure that they are not used for more than one purpose. Okay, further, so we've talked about XVIO, and now we're going to talk a little bit about some of the settings that are also important to DPDK applications. So systems, DPDK in particular, allocates memory for its drivers and for the packet transport, and it uses memory allocated from huge pages. Linux allows you to allocate huge pages in different sizes, and it's advantageous to use huge pages that are larger in size, because when the system needs to map a virtual address to a physical address, it has to go through a process where it has to do that lookup. And if there are smaller huge pages, then there are more of those pages, and the lookup has to look up from a larger pool. If you allocate larger huge pages, typically 1 gig huge pages, the number of possible huge pages is smaller, and that lookup is faster. When you allocate memory, you also need to ensure that you allocate sufficient memory for the various different. Just like we partitioned the CPUs between different tasks, you need to partition the memory between different tasks and ensure there is sufficient isolated memory for the different uses. So the preference is to use larger huge pages if you're running DPDK applications. We talked about extraneous interrupts, and there are other sources of interrupts that you need to isolate as well. So we talked about system management interrupts generated by the server, by the BIOS. But in addition to that, the operating system has many tasks running that generate interrupts for various things, timer interrupts, and so on and so forth. And it is necessary to isolate those as much as possible away from the data path. So there's a couple of techniques that are required here in order to do that successfully. First of all, Linux tries, by default, has this process called IRQ balance, which will spread interrupts across CPUs, or more specifically, it will direct interrupts to CPUs that are underutilized. So it tries to spread the load across the different CPUs. The effect of that is that if you're trying to run a high-performance traffic generator, or you're running a VNF, and you've got some lull in traffic, Linux may well decide to direct some interrupts to the place where you are trying to run your data plane traffic, and the net effect will be that it will cause an interruption in what you're trying to do and some packets to be dropped. So the typical approach is to, first of all, is you disable IRQ balance process so that it does not scan the system and spread interrupts across the different CPUs. However, that is not sufficient to control what is going on. In addition to that, once you stop the IRQ balancing process, you need to also configure the system to take the interrupts from whatever location they are and steer them to the CPUs that you have designated to handle all of these miscellaneous interrupts. And those CPUs should not be the same as the data plane CPUs. So we're not going to go through this particular example in detail, but what we've described is turning off the interrupt balancing Now, proc interrupts gives you a picture of interrupts versus CPUs. So the picture here, of course, is a bit of an eye chart and is very difficult to read, but it is essentially interrupts on the left versus CPUs. So where you have this large matrix of where specific interrupts can be handled and which CPU they're handled on. And the typical approach is to go through and ensure that all CPUs that are possibly generated and landing on a data plane CPU are reconfigured to be handled by the OS designated CPU or other CPU that is designated for miscellaneous management tasks, but not the data plane CPUs. Now, we're going to touch upon another point here, and this relates to both interrupts and to iPerf testing, and illustrates why using something like iPerf is a little bit more complex than might be readily apparent. With DPDK-based applications, they're using a poll mode driver, so they're bypassing the operating system for a lot of the packet handling. If you choose to use something like iPerf and you're using the traditional Linux network device, the packets are going through the Linux kernel to be handed from the network port up through the Linux kernel up to the application or VNF itself. If you do nothing, the typical path is something like what we see on the left here, where the NIC will generate, will receive a packet, put it into its buffer. The bottom part of the network interrupt handler in the kernel will take that packet and feed it to the top half of the network stack, the non-interrupt driven part of the network stack. And then that network stack will determine which process, which user application it needs to go to, and will copy that packet to the appropriate process's buffer. The problem with this process is that the lowest level of interrupt handling could happen on CPU 1. The OS part of the processing might happen on CPU 2, and the user process might be running on CPU 3. And each of those transitions incurs a cost in context switch and possibly in packet copying. So by default, this is what you get. It's costly, and that cost is not apparently visible. So there are two facilities within the system to try to optimize this. One is called receive packet steering, where the system will try to localize the network processing part of that processing for the low-level interrupt handler on the network stack portion of it. You can supplement that further by enabling receive flow steering, which has the effect of trying to ensure that as much of the processing as the Linux can control is done on a single CPU, is done on the same CPU as the process that is eventually going to receive that packet. Now, while this all sounds like it might be a small amount of overhead, when you get to handling large data rates with iPerf type traffic generators, these can have a dramatic impact on the amount of throughput that you get, because the handoff between CPUs and the control of which CPUs get what becomes very important. It's very easy to overload the network stack portion of it or other portions of it and have the CPU being the bottleneck in that data path. So we're not going to go through this in any more detail than this, but this is very important for iPerf and NetPerf type benchmarking. And we talked a little bit about the benchmark, the interrupt management and settings. Now those similar things apply to interrupts, and VMs. Okay, going on to the next section where Christo is going to walk through an example of running benchmarks against Agilio OVS.
Yes, thank you very much, Pervez. So what we're going to do in this example section is taken what we've already spoken about in the webinar. It's the host and VM configurations, it's testing topology, and then taking the NUMA architecture, doing the CPU isolation, and performing some tests. So the test goal for this scenario that we're going to explain is to verify layer 2 forwarding performance of a specific VNF. So it tests the entire data path, including virtualization. So you can see in the topology diagram on the right that we've got the hypervisor included as well. With that, there's a lot of questions that need to be asked. It's like, is the VNF going to be the bottleneck? Is the PCIe bus going to be the bottleneck? Is the SmartNIC going to be the bottleneck? Is the SFP going to be the bottleneck? Or is the Open-NFP switch going to be the bottleneck? In this testing topology, I took the guest operating system having a DPDK application L2 forward running, and then I kept on increasing the number of VMs until I got to a portion where I could actually reach my testing goal. So it was an iterative process to ensure that I can get to a portion where I test the capabilities of the SmartNIC correctly. In the testing topology, as we've previously discussed, this is the host to VM to host scenario where we used an XR traffic generator as an external traffic generator connected to a single machine that's got a SmartNIC included and then multiple VMs running. So during the allocation of the CPU, the first step that you need to determine is that you've taken your SmartNIC, you've plugged it into your server, and now comes the next part. What CPUs do you need to use for this testing? And what one can use is the lspci command to find out the PCI address of the SmartNICs that's included, and then use some of the sysbus PCI drivers to find out on which NUMA node the card is allocated. So in this example, the card was installed on NUMA node 0, and the CPUs that is highlighted in yellow currently is the local CPUs for NUMA node 0, and it's all of the even numbers. It goes from 0,2,4 and all the way up to 46. So in this slide, again, we've got the same topology that's been exported using the ls topology command, and we've highlighted the different portions again with some more details in this case. So for the CPU allocation design, we've given for the host operating systems the CPUs 0 and 24, which I've indicated together as they are part of the physical core and are hyperthread partners, and CPU 1 and 25. Now you'll notice on the image that we have is that 1 and 25 is part of the odd number CPUs, and they're actually allocated on the right-hand side. So for some of the operating system tasks that's not critical to the performance of the test, that can run on the other NUMA node that's not being used for the fast data plane. We have again used the isolation of all of the CPUs that's not been selected for the host operating system, and that can be seen with the CPUs that's highlighted in the black box. We've given the Netronome Vert IO relay 4 different cores, again 2 and 26 and 4 and 28, which are hyperthread partners, and then 4 VMs. So during the testing, I first tested with a single VM, then with 2, then with 3, and then with 4, to ensure that I could see the per VM scaling and see an increase in performance just by increasing the number of VMs to ensure that I can saturate the SmartNIC data plane to get the desired test results. So as some more information on the VMs that was used in this case, we can see that there was 4 CPUs being used from the output of this diagram, and then also 4 gigs of RAM and 2 ViRT-IO interfaces. Now, 2 different CPUs were allocated for each of the VMs to run a DPDK L2 forwarding app to be able to take traffic from a single interface and pass it through into the other interface. And that's why we've dedicated 2 CPUs from each of the VMs for the data plane processing. So if we go back to previously in the webinar when we talked about the host and VM configuration, this is again looking at the host boot settings for the hugepages, the isolated CPUs, enabling SRIOV, and some of the power management systems. At the top, there's also the pinning of specific ViRT-IO relay interfaces to ensure that when you run a test, you know exactly where it's being pinned to ensure that you can have reliable results and reproduce the results the next day with exactly the same setup. And that's also, as Pervez mentioned, for the power management settings that's done on the host as well. It's very important to turn off those settings so that there's no power saving mode that would potentially, when running traffic, reduce the your CPU frequency or increase your CPU frequency, which would give you results that you cannot reproduce. So the host boot settings is very important to make sure that you isolate your CPUs, you turn off your power management settings, and you require enable all the necessary features to have the setup working. Then within the VM, as we've previously discussed, you need to disable your IRQ balance to ensure that none of the interrupts that's being used for the TCP IP stack is handled by CPUs that's being used for the data plane and running the L2 forward DPDK application. The last command we've just got there is the communication, or the command we used within the VM to show that we're using the logical core 2 and 3 to run the test in each one of the VMs. So again, this is just the output of a test that was done to test Agilio OVS on a specific SmartNIC. It was the 1 × 40 gigabits per second SmartNIC, and testing overall throughput through the card, including SRIOV and virtual machines. Use the XCR as the external traffic generator, and within the VM using a DPDK app L2 forward to forward traffic between 2 different ports. So Pervez, it's...
Sorry.
I think you might have been muted.
I was. Okay, I was just saying that concludes our talk, but we will wrap up with the conclusions here. In starting out, you need to decide what component you're trying to measure and what measurements you need, and plan your test bed and your setup accordingly. The data rate is going to very much influence what components you use. It ranges from being very easy with low data rates to being very, very critical when you get up to the higher data rates. The most important thing in all of this is isolating the components from each other. Ensuring that you partition and isolate the CPUs is the most critical part of doing any of this benchmarking. But secondary things that are quite important too, but will be less visible, things like turning off the power management, making sure you're allocating memory appropriately, the number and sizes of things like hugepages, and then things that will affect your test, but in less obvious and interesting ways are things like the system management interrupts and other OS-generated interrupts. Those need to be isolated and steered to CPUs that are not running data plane traffic. So isolation and partitioning of resources and ensuring the system is running at maximum speed for any of these measurements are the key factors. So that concludes our talk. There are some additional slides at the end that we did not present, but that cover different topologies that you might use to go into a little bit more depth on the variations on test topologies. Thank you.
All right, so we do actually have one question for you guys. What is your experience with using one hyperthread for a high-performance DPDK application and then using the hyperthread sibling on the same physical core for another application, high performance or not, regarding the performance of the first DPDK application?
Pervez, do you want to take that one, or can I go? So from my perspective, what I've seen previously using hyperthread siblings is it doesn't give consistent results. We've had scenarios when you test the hyperthread partner and the sibling to send and receive using different DPDK PAL mode drivers and get great results when some of the packets are in the layer 2 cache, but in most of the other scenarios, when using the hyperthread siblings, we've run into performance reductions in those scenarios. So our goal most of the time when running DPDK applications for high performance testing is to steer away from using the hyperthread partners when setting up testing topologies.
Yeah, I'd agree with that. And remember that the hyperthread peer CPUs are sharing some degree of logic, so there is interference in the tasks that they are performing. And in the best case, you'll get rather small interference. In the worst case, you can get very significant interference. We've had cases in the past where we've observed statistics gathering being done for applications on the hyperthread CPUs that have a drastic impact in resulting in dropped packets on the data path. So it depends on how much you want to control it and what your data rate is as to whether it's tolerable to use the hyperthread peers or not.
All right, thank you, Pervez and Christo. This webinar, as well as our previous webinars, can all be found on the classroom page of the OpenNFP.org website. Thank you, everyone, for attending.